Right now. Hello, everybody. I'm Juan Carlos Curi Pinto. Today I'm gonna talk. Can you hear me, Bravo?
Yes, we can hear you.
Yes. This talk is supposed to be interactive, so only you can talk, and you will be the one who asks the questions of the audience. So you can interrupt it at any time, no problem, because it is totally interactive, the presentation. Today we'll talk about deep reinforcement learning, or DeepRL. Here is the link of the slices. Let me admit more people. Mm, okay. And here is my LinkedIn account in case you want to know more about my career. I'm a Master of Science in Computer Science with a major in Machine Learning. I'm graduated from the OMSCS, Georgia Institute of Technology. Mm, admit all. Okay, we'll continue. Um, is everything clear, Bravo? You can see my presentation.
Yes, everything is clear. Just go ahead.
Are you recording it?
Do I have to record?
Yes, if you
Or
can,
you're like,
please record.
okay, just a
Here
minute.
I'm recording locally. Okay, I'm also a computer engineer related from SPOL. Nowadays, I'm a senior mentor of 7 Udacity nanodegrees. Uh, they are intro to self-driving cars, computer vision, artificial intelligence for healthcare, self-driving car engineer, machine learning DevOps engineer, sensor fusion engineer, and C++ developer. Okay. I will be the future CTO of Next Synapse, which is a robotics startup in Switzerland. We are supposed to build a self-driving wheelchair controlled by the mind via an encephalogram. And I am an independent researcher since 2002. I research artificial general intelligence, neuroscience, and mathematics. Um, I also graduated from the Deep Reinforcement Learning Nano degree. Here is my diploma, here is the certificate, and here are the 3 projects in case you want to see the code, the 3 projects of the nano degree. Navigation, continuous control, collaboration, and competition. Okay, you can download these slices from this link here, the parallel tree. Wait a minute. Okay, and what is deep reinforcement learning? Deep reinforcement learning is a synergism between reinforcement learning and deep learning. Uh, in traditional deep learning, we have an environment, we take actions over the environment, and we observe the state. And we also obtain a reward from the actions and the states. That's the traditional approach to reinforcement learning. However, deep reinforcement learning adds a neural network to represent the state, complex states, not only the Greek world states, but complex states that could be anything, could be pixels in a screen, or could be sensors, anything. Uh, as I said, deep learning has two families of algorithms: the family of reinforcement learning and search algorithms, and also deep learning. Let's examine the first family: search algorithms and reinforcement learning. Search algorithms are um, uh, general problem solvers in which each state is a state of the world, and there are links, causes and effects, in which we take actions and we transition from one state to the other, and that's the way we search for solutions in a pattern space. Um, the reinforcement learning is very similar to search algorithms, but it has a powerful mathematical formulation in which probabilities and rewards are expressed. For example, if you are in the state S1, you can transition to state S3 via this action A2 with a probability of 1 and a cost or a reward of 3. Um, we have this is the mathematical formulation, which is a very solid mathematical foundation. You can even take a course in reinforcement learning because there is a lot of mathematics behind this theory, behind this algorithm, and it is mathematically proven. There are many proofs that it really works and it is optimal. Um, we have also other families of the same family of algorithms has another branch, which are the Markov models for perception. Okay. Um, we have Markov decision processes for action and Markov model for perception. For example, here is the Viterbi trellis. The Viterbi algorithm solves the Markov model. And here we have the Viterbi trellis for phrase level recognition. Here we have words, and this is a very limited vocabulary. However, the amount of neuron-like elements and vertices they are very similar to neurons and axons. The amount of connections and nodes is incredible for this little problem. Um, we have this is small classification. Depending if we have control over the transitions, we have NDP or Markov models, and if the states are completely observable, we have, for example, hidden Markov models, PondP, when the state is not partially observable, and we have the traditional formulation, the vanilla NDPs and Markov change. And deep learning is perfect for solving POMDPs and HMM, hidden Markov models and partially observable microdecision processes. I mean that, for example, if you have a partially observable problem, deep learning can help you solve this kind of partially observable problems with a very decent time. whereas if you solve it mathematically in the traditional way, it's computationally intractable. However, deep learning learns a good enough approximation of the solution of the problem in a decent amount of time, which is computational tractable. Here we have Markov decision processes in Greek world. Here are some video games I programmed in my master's in machine learning. A very interesting video game. Here we have a very interesting video games with vampires and letters and mazes and goals and an explorer which is supposed to obtain this diamond. And this diamond propagates the reward through all this path, believe it or not, because the mathematics of reinforcement learning predicts this behavior. The reward is like flowing through the nodes. In this way also, we have the mouse, the cats, and also the cheese. The reward is propagated through the states, and the codes, in this case the cats are negative rewards, are also propagated. So you avoid the dangers, like the cats, and you try to find the food. These mathematics work perfectly in Greek world, but what about bizarre state? Can we use fuzzy logic or something else? When we have a complex state, deep reinforcement learning comes to the rescue. So, for example, if we have a video game in which we have all the pixels in the screen can act as the complex state, and we take some actions with the joystick. And this is how DeepMind technologies solve the problem of playing Atari video games by connecting to reinforcement learning a complex state which is represented as a convolutional neural network. And by plugging a convolutional neural network, the reinforcement learning algorithm is able to understand the complex state of the video game. And the formulation of this is very simple, because you have the loss in this case. It's a little bit complicated, but at the same time simple. I mean that if you have the loss of, for example, the Q-learning algorithm, you translate this loss to I'm sorry. You translate this loss to you transform this problem into a supervised learning problem. And once you transform the deep reinforcement learning problem into a supervised learning problem by doing this trick, you apply only gradient descent, which is a very famous algorithm and a very powerful one. And basically, you are solving the deep reinforcement learning problem by transforming it into a supervised learning problem, like a traditional deep learning problem, by using this technique of gradient descent, in which the error is represented as a curve, in which the high peaks of the error means high error, which is grown, and you are supposed to descend to the least amount of error in the local optimum, and you repeat until convergence. This gradient descent, uh, you are you are minimizing the loss function through time, and eventually you reach convergence to a local optimal. And when you do so, uh, your agent is supposed to achieve a state of reflexivity. I mean that it's like, for example, when you practice a sport, any sport, for example, running or basketball or football, anything. When you practice a sport a lot, you it's like the neural networks in your brain adapt to the game, and eventually you play. You achieve competence without comprehension. You basically act reactively. For example, you never think if if for example you have to move it in this way or in this way, because you act by reaction, you act by reflexes. This is the moment when you achieve reflexivity, and this kind of algorithm is an artificial reflexivity. Uh, is deep learning inspired by biology? For example, we have here the traditional perceptron, which is very simple. We have the step function, the weights that represent the synapses. However, in biology, it's a little bit different, because we have the SUSE model and uh, the Hawking and Huxley model. Uh, we have which have spikes and bursts and action potentials, etc. Now, there are many things that the traditional perceptron don't model. However, we can say that yes, deep learning is somewhat inspired by biology, because here we have, for example, the mathematical model for in the Hawking and Huxley model, which is a differential equation in which the action potentials and the voltages and the synapses are represented to numbers. It is a dynamical system that mathematically um, represents this kind of spikes and everything in the brain. However, if we take some assumptions, for example, we say that the time is limited to this, and the action potential is this, and everything, you finally obtain from by using the Huxley model and the SUSE model, you can derive the actual mathematics of the learning. So we can say that deep learning is a special case of the biological neurons, and I studied this in the computational neuroscience course at Coursera. Let me enter people, and we can continue. So far, do you have questions? Okay. Can you hear me?
Yes, we can hear you.
Okay, you can see the slices and everything is correct. Okay. Neural networks are both discriminative classifiers and generative classifiers. For example, if if we have two families of classifiers. We have, for example, discriminative classifiers, and they are supposed to divide the pattern space into regions by using a frontier. And this thing requires less parameters and less memory, because the discriminative classifiers only model the frontier of a pattern space, the frontier in which we divide the pattern space. Examples of discriminative classifiers are the perceptron. For example, the perceptron divides the pattern space in two parts. We have this algorithm here. And we also have generative classifiers. For example, we have k-nearest neighbors, and they are generative classifiers are supposed to model the stereotype. And when they model the stereotype or the pattern, the stereotypical pattern, they require more parameters and more memory. However, they are like competitors, but an example of a generative classifier is when you classify something by generating the stereotype. Okay. In the middle we have neural networks, which are discriminative and generative classifiers. For example, we have the autoencoders that model both the frontier and the stereotype. They have a decent amount of parameters and memory. For example, we have this this autoencoder, which is supposed to take an image as an input and output the same image, but only they reconstructs in feature space. For example, the GANs are a good example of this, because they generate the patterns. So they model the frontier of the patterns, but also they model the stereotype. And neural networks are like belong to the family of eigenfaces, PCA, principal component analysis, independent component analysis, and it is very interesting because, for example, if we examine eigenfaces and also the output of autoencoders and GANs, generative adversarial networks, we observe that the patterns learned from this kind of algorithms is more beautiful than the actual patterns, the actual instances, and that's something provocative, because it provokes thought, it provokes philosophy behind it, because we can say that beauty is like the beauty is like the least action principle and the least resistance applied in the brain. It's like, for example, if you have learned a lot of phases through your life, and those phases that are average, that they are closer to the stereotype, they are more beautiful than the ones that have protuberance, the ones that have exaggerated patterns. For example, a big nose is not beautiful, or for example, a big mouth, um, which is outside the proportions. The proportion is the beauty. So we can mathematically express beauty in terms of this kind of new statistics that deep learning provides. Uh, it's like if you have developed a pattern, it could be a pattern of everything, but for example, in the case of faces, if you watch an actual face against the pattern you have in the mind, if the pattern you are seeing provokes the least resistance possible, it is considered beautiful. However, if if something goes wrong, there are something that it is not in accordance to the pattern that you have learned. Perhaps you don't perceive that particular face or pattern in a beautiful like a beautiful thing. Um, it's a little bit difficult to explain, but the mathematicals is something in which you can model mathematically the beauty. And how how and why deep learning works. Here is my essay. Here we have an essay how and why deep learning works. There is an essay I wrote for the Spike. Um, we have homeomorphisms, so our projections toward lower dimensionality spaces. I was inspired by this blog here. For example, we have a pattern here, which is in Euclidean space, and by using neural networks, we learn how to deform it, and we can in another space, which is lower dimensional, it can be separated by using a line. So basically, deep learning works because it projects patterns in high dimensionality pattern spaces toward lower dimensionality spaces, and this projection takes advantage of the most salient features that represent the pattern in a statistical way. You can read my essay in case you want to know better.
Okay, so there is two questions. So if you want, we can proceed to the questions first, and then we can continue with the slides.
Yes, the question.
Sure. So the first question is, apart from gaming and self-driving car, what are other sets of problems which reinforcement learning can be applied?
Yes, that question will be answered at the uh, in the next slices, because there are many slices in which there are many examples of how deep reinforcement learning can be applied.
Okay, and another interesting question I got here is, can you tell us a bit more about research perspective in neuroscience and deep reinforcement learning?
Neuroscience. That's another question that will be answered. Here we have homomorphisms. Here we have a very beautiful explanation of what's happening in the brain. It is part of my thesis, and it is based on neuroscience. Here we have a very interesting explanation. and I will explain it in more detail when I arrive to this slide. Okay,
Yeah, sure.
let's go back to homomorphisms. It is already explained. Uh, Deep learning is like a funnel that generates common features among patterns. This is a new definition of abstraction. It's like if you have many patterns and you extract the common factor. It's an analogy. However, this is more alchemy than science because there is no mathematical proof yet. Uh, it is cargo cool science because biological neural networks were imitated without fully understand them. Um, ho- this is a very interesting explanation. Homomorphisms toward spaces of less and less dimensions that are mapped in a continuum. It allows to make analogies in a continuous space of features. Features are generated automatically, unlike other algorithms of machine learning. It's like if deep learning acts like a funnel. This is the funnel, and you are projecting patterns from this high dimensionality space to a lower one, to a lower one, to a lower one, and finally to a classification. And this is projecting probably in Euclidean space, or in the space of sensors, or in the space of words, or anything that deep learning can handle, and is projected to this feature space. And when you project something to a feature space, this projection is continuous, and hence you can analogize by through the continuum, because if something goes in some feature resides in that particular point in feature space, a high dimensional point, which is the activation of features. Um, Similar features are projected in a similar pattern, so you can analogize. For example, similar features will be projected in the same region of the feature space, and that's why we can say that deep learning can analogize, and this is very powerful because if we read, for example, the Surface and Essences of Douglas Hafeter, the last book of Douglas Hafeter, analogies are flexible thinking and extrapolation and avoidance of type 2 errors. However, we increase the type 1 error when we analogize. It is not an exact way of thinking, but we can predict how the world works, even if we don't have exactly the same situation. The combinations of patterns we can see in the world is super high. It's like when you combine patterns, the combinations explode exponentially in the number of patterns. So we cannot have the very same situation all the time. So machines should be able to analogize in order to understand the world. Otherwise, it's like, for example, if you have a door which is not exact at the door of your home, you can infer that that door behaves in a similar way, even if it is not the same size or the same color, but you have an idea, a pattern in your head of how doors can work, and how can you operate doors to open the door, close the door. if, for example, in traditional mathematics, for example, mathematicians are um super obsessive about numbers and super obsessive about obtaining very precise very precise approximations to many decimal places exact. However, this is not how the world works, because, for example, let's say if we want to detect to understand how a door works, and, for example, if the door doesn't have the same illumination, or if the door is dirty, it will be slightly different, and your algorithm should be robust enough to deal with the difference, not to be exact. If you are exact in your mathematics, you are it is a brittle it is a brittle solution. It is not robust. Analogies make the reasoning of machines softer, more open-minded, more robust, less brittle. Okay, and the entire effort of artificial intelligence is essential a fight against computers' rigidity. And this very book here also explains that analogy making is categorization. And we have plenty of algorithms to mathematical formulations of categorization. We have deep learning, we have all the classifiers in machine learning that do categorization. So analogy making is categorization according to this book. And in the book you can read at the end that analogy making is exactly the same as categorization. And we have plenty of algorithms in artificial intelligence and machine learning to do so. We have no okay we have in deep learning we have nonlinear activation functions, and these work for two purposes: to make the mapping nonlinear as real world problems, and to cut bizarre regions of the pattern space. For example, if you represent problems like PCA does, principal component analysis does, you are representing problems in a linear way. You are assuming that your problem is linear. However, real world problems are not linear, and when you have a nonlinear function, you are making your neural network able to deal with nonlinear problems, and this is important. And also, the nonlinear function acts like a switch. This, for example, this region belongs to this part of the pattern space, and this not. This is part of the frontier, and this is not. It's like a switch. The activation function. We have the ReLU, we have the sigmoid function, the many non-linear functions. Okay, and here we have the what we can represent with one layer of neural net of neurons, with two layers of neurons, and with three layers of neurons. For example, with one layer of neuron, we can only represent a line, a frontier, which is a line. With two layers, we can have two lines. And with three layers, we can have arbitrary regions in the pattern space. So there is a there is a theorem, the Sibvenko's um, universal approximation theory, which states that if you have three layers of neural networks, if you have three layers of neurons, you can represent any kind of pattern if you have sufficient neurons in each layer. Um, and and we can see the expressive power of deep learning, of deep reinforcement learning. In one hand, we have the Sibenko's universal approximation property of artificial neural networks. You can read this paper, Sibenko 88. So the pattern represented by the complex neural network in the algorithm can represent any kind of pattern. Deep learning can represent anything. Deep learning, we have probably an infinite amount of applications of deep learning. Because deep learning can process multimedia, can process text, can process anything, robotics. It can handle anything because it is very powerful and very expressive. On one side, we have the Sibenko universal approximation property of neural networks. And on the other hand of the algorithms, because deep reinforcement learning is composed by two kinds of algorithms, neural networks and search algorithms reinforcement learning. We have the general problem solving. And when we state that search algorithms are general problem solvers, we are not exaggerating because this family of algorithms can represent any kind of problem and can solve any kind of problem. So many people, like the guys of DeepMind says that reinforcement learning is enough to reach general artificial intelligence. In other words, they believe, and I also believe, that deep reinforcement learning could probably solve the general problem of artificial intelligence, or AGI, artificial general intelligence. On the other hand, we have another family of algorithms which are also compatible with deep reinforcement learning, which are the recurrent neural networks. And recurrent neural networks are also general computers, because if you visit the website of Jürgen Schmidhuber, a Swiss computer scientist, he already proved that recurrent neural networks are also general computers. In other words, you can represent anything with recurrent neural networks, and they are compatible. And I will talk about recurrent neural networks in the next slides. So deep reinforcement learning is a very powerful artificial intelligence algorithm. Okay, here are some of the applications that the previous question. How can neuroscience be combined with deep reinforcement learning? Okay, here we have here is the development for algorithm. Development for algorithm is used to route packages through the internet. But I also discovered that this kind of algorithm is also able to handle any kind of problem, especially in robotics. So I wrote my undergraduate thesis in by using this Bellman-4 algorithm, and I created a model of the unconscious of a robot, and the robot is supposed to learn how to move the joints and the actuators in order to move coherently in the world. And this is a matrix. These are four-dimensional matrices. These algorithms work with four-dimensional matrices, and if you connect these matrices like the connectivity suggested by the Bellman-4 algorithm, you obtain these. It's like all algorithms have memory pointers and have pointer have memory structures, and if you connect all the memory structures with pointers are I like the arrows here, and you can draw the connectivity of the algorithm, and this is what I obtained for this is the geometry of this Bellman-4 algorithm, and this is a reinforcement learning algorithm, which interacts with reality, uh, and this part here is very similar to this part here. So, for example, we can say that this is the by the way, these are the cortical columns in the brain, which is a sorry, which the cortical columns in the brain are are a common connectivity pattern in neurons that is repeated billions of times. We have billions of these neural processors in our brains, especially in the neocortex, and this pattern is repeated all over the brain, and this is how neurons compute our perception and create a map of reality, our consciousness, and this part here, the way it connects is very similar to L1, which is it has 6 layers, layer 1, 2, 3, 4, 5, and 6. But layer 1 is very similar to the way this reinforcement learning algorithm is connected, and we have 3 layers more. We have the 3 layers of Sivenko, the Sivenko's universal approximation theorem. All right, and this is highly speculative. But I read it in this book, Neurophilosophy, which was written by Dr. Rodolfo Ginás, the author of Tensor Network Theory and the cerebellum chapter. He is an expert in cerebellum, and he created a mathematical model of the cerebellum by using the tensor network theory, which are very similar to actual neural networks and controllers. And he, in his book, explained that uh, 3 layers are required. 3 layers are present but I didn't understand at that time. But once I learned from deep learning and the Sivenko universal approximation theorem, I started to believe that perhaps here these 3 layers represent the complex states of this region. However, L6 is connected to other parts of the brain, to other regions. So it's a little bit complex to explain this. We can talk hours and hours about this topic. Um, layer six, layer six is how the connectome is formed, because layer six connect to it has projections from and to other uh, other region or other brain regions, and these are the other brain regions. Sixth layer connects forms this connectome. Layer six is how the brain connects to other parts, and this special connectivity has been mapped by Fuster, and he created the Fuster cognitive theory. Uh, el, and Fuster stated that we don't have we don't have a grand we don't have grandmother neurons. Uh, we have the brain is wired in the other way around. It is wired upside down, like inverted overlap pyramids. Each pyramid corresponds to each modality of the sensation, which is projected and has overlappings with other pyramids and form associations in these associative areas of the brain, both in the perceptual memory behind the brain and in the executed memory, which is the frontal lobes. Uh, and they are all connected. Everything is connected to everything in this hierarchy. Um, Look, that this is very interesting because traditionally we believe that this is the way brain are connected. All artificial intelligence researchers believe that uh, pyramids are like this, but it is that's not the way the brain connects, and this is why artificial intelligence developers fail, because there is a misconception, and neuroscience sometimes can teach you how to improve your artificial intelligence. Um, this is these slides were written by me 2 years ago, and this is kind of like a prediction because I will read it. Natural language processing requires wide learning and massive parallelism. Fuster cognitive inverted overlapping pyramids, grand mirror neurons, and horizontal projections. Horizontal projections and wide learning. Horizontal projections are the recurrent neural networks, and nowadays we have an explosion of recurrent neural networks for natural language processing, and they are successful. We have many many recurrent networks, the transformers, for example, GPT-3, uh, BERT from Google. China also have another transformer with billions of parameters, or trillions of parameters. Um, and this was an accurate prediction of me 2 years ago. And here I state, is this a solution for unsupervised learning? Yes, because those natural language processing systems deal with unsupervised learning, deal with unstructured data from text. And here says horizontal transformation of the same pattern. Um, uh, yes, it's like that's difficult to explain, but it's like you have transitions of patterns, and you don't have to model only the abstract pattern, but many transformations of the same pattern. It's for example, when you watch something from different perspective, or you observe a pattern through time, how it evolves, and this kind of thing are represented in the brain as patterns in the same level of complexity. Same level of complexity means horizontal. Okay, and we continue. What are feelings? Uh, when 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 we were when we were at the state of being reptiles, um, at this stage of the evolution, uh, we have the reptilian brain. The reptilian brain are the subcortical structures in the brain, the amygdala, the the and you need to go inwards. Inwards is the subcortical direction, which is more reactive, more instinctual, more invariant, more sentimental. Abstractions of cognitive aspect of common to the species. Um, I mean that the pattern stored here are common to the species, the feelings. For example, the fear of heights, the when you avoid something that you dislike, for example, feces. Uh, you dislike it for a reason. And for example, you like something, for example, an apple because it's juicy and it's good for your health. And the brain captures this kind of invariant in this region, in the inner parts. However, the outward direction, the cortical direction, is more proactive, more learned, more flexible, and neuroplastic, more rational. The abstractions of experience of an individual life. So these invariants are corresponded are these invariants correspond to the life of an individual. It is not something related to the species. It's something related to the life. You learn through the life. However, this region here is more sentimental, more invariant, and it relates to the species. And many people think that hearts generate feelings, but that's wrong because we have an artificial heart, and the people who have artificial hearts still have feelings. The heart is just a pump, and we can replace it. However, we cannot do the same with the brain. If you replace the brain, you're replacing your feelings. If you replace your heart, nothing happens. This chapter is very interesting. Learning inverses instead of deducing them. For example, here we have a robotic arm I modeled mathematically in my thesis. And here I deduce the Lagrangian mechanics, the differential equation of this mathematical model of the robotic arm. And you can see that it is a very complicated mathematics, very difficult to understand. And the point here is that if you obtain the inverse if you obtain the inverse of this mathematical model, you can actually control the arm in a very sophisticated way. However, obtaining the inverse of this kind of problem is probably impossible because some differential equations don't have as a symbolic solution. Maybe you have to iterate and obtain a numeric solution for each specific uh, uh, situations, for each specific state of the dynamical system. Uh, this is very complex. However, um when animals need to move, they never go to the university in order to move. For example, you have a recently born gazilla, a gazilla just born, and the gazilla can walk immediately. Uh, in few minutes after the gazilla is born, can walk. So the gazilla doesn't need this kind of mathematics. Doesn't the gazilla doesn't need to go to the university in order to move, or to hear or to see, because the mathematics of audition and vision are also complex. The gazilla can immediately walk and can immediately avoid the lion that tried to devour the gazilla. So learning inverses instead of deducing them is the solution that nature provides for any problem of intelligence in general. Um, it's like you learn um, you 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 learn you learn the solution that works. You try many solutions, and if a solution works and move you from this state to this state, you learn it, and you don't need to understand how it works. You become competent without comprehension, and that's the way the subconscious works and intuition works. The We have two approaches to artificial intelligence: the rationality approach of reductionism and science, and we have the holism and intuition. And the intuitive approach of deep learning is the winner, because rationality cannot deal with real life situations. Uh, sorry. We have the subconscious, the reflexology, and intuition, which are the opposite of deduction and rationality. Correlation does not imply causation, but it helps to infer causation. This is important because in the world you can see many correlations, and when things are correlated, are probably causated. Uh, there is probably causation in this. Okay. We have other kind of problem apart from robotics. For example, in acoustic, there are probably 10 world experts capable of modeling human speech and room acoustics. In acoustic, you have similar differential equation systems, similar dynamics, also in vision. And there are a few experts capable of dealing with this kind of problem, because you need functional analysis, you need very complex mathematical tools to understand this. However, you can learn the solution, an approximate solution for this. So if you really want to solve this kind of differential equation systems, why not solving the differential equation system for learning instead? For example, we have here this paper which explains how to solve deep learning per se, the differential equation system of deep learning. And if you solve this kind of differential equation system, you can make deep learning many orders of magnitude faster. You can read my essay. I wrote this essay. So if you really want to solve things exactly, why not solving deep learning per se, which is very complicated, as you can read in my essay. And now we begin the applications. How we can apply deep reinforcement learning to the world. We have lunar lander. You can see this video. Lunar lander learns to operate this ship, this aircraft, to land in the moon in this video game, and it learned from scratch without teacher, only by trials and errors, many trials and many errors. Here is the learning curve. The learning curve is a sigmoid. It is exponential at the beginning, then suddenly becomes an expert, and it is there is an exponential asymptote at the end. Sorry. And here the engine, the aircraft is crashing and crashing and crashing and crashing, and then it begins to operate in a decent way. And you can see this video. It's amazing how this aircraft moves like an animal. It doesn't move like a traditional robot, at least the kind of robot we imagine in our minds. It moves very smoothly. It adapts to the continuous nature of these kind of differential equation systems. Okay, and this system, this learning system that was capable of learning how this aircraft works, was programmed in 200 lines of Python code. We can say that differentiable programming is a better programming than all humans. I mean that if you apply deep learning and gradient descent to any kind of complex problem, if you have sufficient data, it can easily outperform any programmer in the world. And that's not an exaggeration. It is an actual fact. For example, I have tried to write controller for this kind of problem and for this kind of problem, the robotic arm, I try to program by myself how to control this, and I fail miserably. However, 200 lines of Python code were able to learn how to control this kind of robots, and also they can learn how to how to obtain patterns from big data. For example, if you have big data like Facebook, like Instagram, you have many images, videos, and they are learning from these images and videos, and they learn better than a programmer. Uh, I know that humans have the ability to see, but I'm talking about uh, the capability of a programmer to express that intelligence in a computer. I mean that machine learning is far more capable of many programmers in expressing uh, how to capture the intelligence in the data. That's and and that kind of things make us dream about metaprogramming and radical machine learning. If anything can be learned separately, then everything can be learned together. For example, we have many examples of narrow AI systems, but if we have enough examples of particular AI systems capable of doing many things, why not dreaming about a radical machine learning system that is capable of learning everything? Um, there is also a myth in artificial intelligence, the myth of the God programmer. For example, many people think that uh, we will never build artificial intelligence because no programmer is capable of programming all the expressions of intelligence in a system. But that's a mistake. Programmers are supposed to build system capable of self-programming and learning everything from scratch. Um, that's why it is possible to build artificial general intelligence. And I predict that AGI or artificial general intelligence will have at most 20,000 lines of CUDA code or C++ code. Um, because we are not supposed to program the expressions of intelligence, but the intelligence per se. We are supposed to build a system capable of learning. We are not supposed to build to program the expression of intelligence. The expressions of intelligence are supposed to be learned from the system. Otherwise, it's impossible to do so. And that's why I believe that the, a solution for AGI should have very few lines which are capable of doing everything. Um, and this is the power of abstraction. For example, this deep informal learning is a simple idea that explains a wide range of phenomena. It's like evolution by natural selection. Both ideas are easy to learn, but their predictions are hard to understand. I mean that their predictions are, for example, if you learn evolution by natural selection or if you learn deep informal learning, those ideas are simple, but the kind of thing they are predicting is very complex because evolution by natural selection predicts everything in biology. And for example, deep informal learning predicts everything in robotics, for example. And not only in robotics, there are many other applications that I will explain later. And finally, deep informal learning is a form of neural Darwinism. I mean that evolution by natural selection and deep informal learning are somewhat related by neural Darwinism. Okay, more applications. We have for example, buying and selling stocks, machine learning for trading, artificial intelligence for trading. And that's one of the reasons I entered to this scholarship, because I'm taking I have taken many machine learning for trading courses, and I want to build a system capable of buying and selling stocks in the market 24/7, 356 days. Um, this system it should be running in the cloud all the time without failure, because it could represent a failure could represent a loss of money, and it is supposed to earn money exponentially, and that's why I quite interested in learning the cloud. I want to become a cloud expert. Uh, we have another application. For example, we have the Stanford helicopter, which was built by Andrew Ng in his PhD thesis, and he programmed this helicopter to learn all kind of aggressive movements that very few humans are capable of doing. Very aggressive maneuvers. Another application is the self-driving cars. For example, self-driving cars are are a growing industry, a growing multi-billion industry in the world. And if you read this article, you will learn that, for example, many self-driving car systems, many self-driving car technology is powered by deep reinforcement learning, because deep reinforcement learning is capable of doing of dealing with all kind of with all the problems of robotics. If you see a robot moving, it is probably controlled by deep reinforcement learning, because it's the most common algorithm for robotics. And the neural network to represent the state of a self-driving car has like two no like 27 million connections. 20, 27 million connections. It means that it represents a mathematical space of 27 million dimensions. It is very complex. It is a very complex convolutional neural network. Another application is playing Atari with deep reinforcement learning. This is the most famous, one of the most famous applications, because with one algorithm, DeepMind Technologies was able to beat all human players in all these video games. At the beginning, they were played at the human level, some at the subhuman level, at the suprahuman level, some of them. But nowadays, they created the rainbow architecture that that contains many principles of deep reinforcement learning, new algorithms, and they were able to beat all human players in the world in all these video games. All video games are nowadays territory for machines. And Google bought DeepMind technology for 500 million, and here we have the complex state of pi cells the convolutional neural network, and the actions taken by the agent. And here is the brain, in which in 2 dimensions it is projected the states, the complex states of the world in each video game. We have another application, AlphaGo and AlphaGo Zero. The game Go is very special because it was the only video game, the only game that humans were dominant, because humans have intuition, and the amount of combinations of Go states is far more abundant than the atoms of a universe. The possible combination of Go states is exponential, grows exponentially with the depth of the game. And humans were very good at playing Go, and no machines were capable of beating humans. However, recently, a few years ago, AlphaGo beat Lisedol 4-1, right? And this was amazing, because for the first time an artificial intelligence system were capable of beating the grand champion of humans. And after that, another algorithm of DeepMind beat it. AlphaGo Zero beat it. AlphaGo 100-0. It means that it was unbeatable. Unbeatable. It is amazing how one algorithm could be even more monstrous and practically learn from scratch everything. For example, this human player took years to learn the rules of Go, to become an expert. However, this algorithm in few hours was capable of achieving suprahuman level to beat anything in the planet. It's like if you start to play this game against AlphaGo Zero, you know for advance that you will lose. Another application is AlphaZero Master Chess in 4 hours. In just 4 hours of simulations, because AlphaZero plays learn from simulations, you feed the simulations in a supercomputer, and in just 4 hours, AlphaZero was able to beat any human in the planet. Chess is no longer the domain of humans. Another application, the Festus animal robots. We have many kinds of robots, flying robots, swimming robots, terrestrial robots, everything with many kind of different geometries. For example, octopuses, elephant trunks, insects, anything. And deep learning, just one simple algorithm of 200 lines of Python code, was able to learn from scratch how to control this kind of animal robots, and they move very smoothly in a very animal way fashion. Wait. Another application is the optimization of power consumption. DeepMind technologies optimize the power consumption of the Google servers, and they are planning to do the same at the level of a city, London. Another application is OpenAI beat the world champion of Dota 2, which is a very complex video game, a 3D video game with the strategies and many kind of actions, many kind of behaviors, many kind of tools. It is far more complex than Go and chess. As a result, DeepMind technologies beat the human champion of StarCraft 2, which is a similar video game with strategies, complex tools, complex dynamics, complex rules. And this algorithm was able to, AlphaStar was able to learn from scratch everything about this video game at the human level and beyond. Another application is Asimo. We know this little robot is able to manipulate things, to explore the world, to see around us, to listen to multiple speakers at the same time, and it is also powered by deep reinforcement learning and deep learning. We have Boston Dynamics, Atlas, Big Dog, Spot Mini. These algorithms are also controlled by these robots are also controlled by deep reinforcement learning. Here we have an interesting video in which this robot navigates and creates a map of a 3D map of the environment. Sorry. And this robot is also able to do a backflip, which is very difficult. Very few humans are capable of doing a backflip. Here's the video. And we have another application, which is the AWS Deep Research Challenge, in which Udacity partnered with Amazon, and they created the Deep Research Challenge. I was one of the 300 winners of this scholarship. It was a scholarship like the one we are taking right now, but in this case the second phase was granted to the ones that program the car in a way that go as fast as possible. The best times were selected for phase 2, and basically we plugged a deep reinforcement learning algorithm to some sensors. For example, we have sensors in the car, we have the waypoints here, and we have the position of the car, the steering angle, the angle of the car, the direction, the track width, the distance from center, many kinds of sensors, and by plugging these sensors to a reward function, in this challenge, we don't need to program the deep reinforcement learning algorithm. We didn't need to make meta optimization of parameters. That was totally automatic. The only thing that we should do was to calculate, to compute a reward function from this kind of sensors. So we have these sensors here, and we calculate the reward function. For example, if the car is here, you should penalize the car. But if the car is in the center and is aligned with the direction of the waypoints, the reward function is high here. And basically, we only need to program a reward function that rewards good behavior and penalizes bad behavior, like anomalous states. And I was able to program a very good engine that obtained one of the best times in this worldwide competition. Another interesting algorithm that is quite related to deep reinforcement learning is Fourier network search. Fourier was a genius because he created a new kind of mathematics. His algorithm was able to bring life to computers, because without the Fourier transform, we cannot imagine multimedia. All kind of multimedia files are represented to Fourier by using the Fourier transform, and this kind of mathematics was able to represent all kind of multimedia patterns. It brought color and sounds, multimedia to the world of computer science. And also, this Fourier transform is able to find correlations in complex patterns whose dimensions are really abundant and correlated. For example, in computer vision and robotics. And here we have a very nice paper, a very nice publication, compressed network search find complex neural controllers with million weights. It means that if you have a million weights, for example, the pixels in a screen, in a camera, you have sensors, you have actuators, many sensors, and this geometry of this kind of complex problem could have easily million dimensions. It's highly dimensional, and by finding correlations in complex patterns by using the Fourier transform, this highly dimensional problem is transformed into a lower dimensional one, and it finds the correlations. It's like they are causally aligned with the problem, and it is amazing. It works like charm. And here we have the Kurzweil law of accelerating returns. For example, there are many people that are highly skeptical of the progress of artificial intelligence, because most artificial intelligence algorithms are computationally intractable. For example, Solomon induction is exponential in a number of dimensions, and exponential problems are hard to deal with and requires tons of computations, and that's why many people are skeptical. But we should be aware of Moore's law. Moore's law states that each year the power of computers doubles. It means that in 1 year doubles. In 2 years is 4 times faster a computer, more powerful. In 8 years no, in 3 years is 8 times more powerful. And you multiply the exponents of 2. 1, 2, 4, 8, 16, 32, 64, 128, 256, 5, 512, and 1024. It means that in only 10 steps you advance 1000 times. For example, in 10 years, computers are 1000 more powerful than before. And this trend continues and continues and continues, and there is no evidence that this trend will stop. However, Kurzweil have calculated another quantum computer scientist. By the way, Kurzweil is Ray Kurzweil is the the director of engineering of Google, and he controls all the artificial intelligence projects. He directs how things work in Google, and for recently we we saw that Google proved the quantum supremacy, and for example, when quantum computers didn't exist some years ago, many experts were very skeptical of that quantum supremacy was achievable. But a few years ago, Google demonstrated that it is possible to create a quantum computer that to take advantage of the qubits. So these things are very real. These things are basically a prediction of the laws of physics. You cannot contradict the laws of physics. They are very real, and let's calculate what is the potential of a human brain. For example, one human brain has 100 billion neurons, 10 to the power of 11 neurons, and approximately 1000 connections per neurons, and approximately through 200 calculations per second per connection, and that gives us 10 to the power of 16 calculations per second. That's the power of one human brain, right? And one human race is capable of processing 10 to the power of 26 calculations per second, right? Okay, that's an estimate of connectivity, and assuming that the spike means computation, the flipping of bits from 0 to 1 is computation. That's analogous to computer power, but it does not represent qualia and subjective experience. We are talking only about connectivity, not qualia. We are talking about raw computation of a brain. For example, subneural processes are not represented in this estimate. We only representing the spikes per second we can perform, and that's our estimate. And here are some predictions of quantum computing. For example, in 2 years, we will have one human brain capability for $1,000. We are about to reach that level by using GPUs and TPUs. So it is a somewhat accurate prediction. It will become true. In just 2 years, we will have one human brain capability, and in the year 2037, 1 cent of computation will buy one human brain capability. In the year 2050, we will have one human race capability. I mean that if you buy a computer for $1,000, you will have the power of one human race, of all the humans combined. So it is an enormous amount of computing for $1,000 in the year 2050, and that's achievable through quantum computing. That's computronium. That means that you are saturating the amount of computations that you can do with matter. So this exponential progress is exponential at the beginning, and then it is exponentially it achieves an exponential asymptote. It's like a sigmoid. It is not exponential. It's exponential at the beginning. It reaches computronium and then it stays stable in computronium. But there are limits. Computronium is the limit, but these limits are not so limited. Not so limiting. This is the real thing, the sigmoid, but many people are skeptical and saying we cannot grow exponentially forever, and this is not what the transhumanists believe. This is a strawman argument. This is a misinterpretation of what we believe. We believe in this, in the sigmoid progress. And we have some resources to learn. For example, this book is very complete. We have the Deep Informal Learning Nano Degree, and we have many Udemy courses about Deep Informal Learning. And that's it. Do you have questions? Hello?
Yeah,
Yeah,
hello.
hello.
Hello? Is everything okay? Do you have questions in the audience?
I
I
think they
think they
don't
don't
have
have
any
any
questions.
questions,
So
so
thank
Thank
you
you,
for.
Fuan.
Hello, Semi.
Hello,
Hello,
Fuad.
Fuan.
How are
How are
you?
you?
I'm fine.
I
I
just
just
have
have
question
question
about
about
the
the
law
law
of
of
accelerating.
accelerating.
You
You
can
can
go
go
back to
back
the
to the
slides.
slides.
Okay.
Yes.
Yes.
So
So
before
before
the
the
human
human
brain,
brain,
there is
there is
some
some
Prediction.
the
the
first
first
line.
line.
We
We
achieve
achieved
one
one
human
human
brain
brain
capability
capability
for
for
1,000
1,000
amount
amount
year
year
2023.
2023.
Yes.
Please
Please
explain
explain
that
that
part.
part.
I
I
don't
don't
get
get
it
it
well
well
now.
now.
Okay. Here we have the human brain capability, which is based on the amount of spikes we have in each synapse, because we have many neurons and many connections between neurons, which are the synapses. And each synapse operates at some frequency. For example, we have 2000 calculations per second per connection, right? Each synapse in the brain is capable of doing this calculations per second, and we have this amount of synapses per neuron, and we have this amount of neurons, right? And we have an overall a raw number which explains how powerful we are as humans on average. We have 10 to the power of 16 calculations per second. It means one number, the number one followed by 16 zeros, right? That's the one human brain. One human brain.
Okay.
Okay.
Thank you
Thank you
very
very
much.
much.
And one human race is 10 billion human brains multiplied by this potential. So we have 10 to the power of 26 calculations per second. This is the potential of one human race. And we have, in brief, we have two kinds of predictions. In the year 2020, 2023, we will achieve the one human brain capability by using GPUs. The NVIDIA will produce. There are many companies, but NVIDIA is the leading company of GPUs that will produce uh, a computer which is cheap enough as $1,000, yeah, that it is capable of achieving the same computational capability of one human brain for this year. In 2 years, in only 2 years, it is possible to buy this kind of computer, right? And I think it is possible because Kurzweil is very accurate with his predictions, and he's always adapting the the extrapolation he's making. He's always on track, trying to see the market and to see the new kinds of computers, of GPUs and TPUs, and we will surely achieve this capability for $1,000 in this year, in only 2 years, right? And this
Okay.
prediction for the for 2050 refers to the power of quantum computers. the It means that a quantum computer for the year 2050 will be capable of doing all the computation that all the human race can do. And that's possible due to the laws of quantum computing, because there are such things like qubits that are aligned in a quantum way that can produce an exponential amount of computations in the number of qubits you're using, and this trend will continue because it is not only about creating, for example, a laptop with a quantum computer, but there are many articles that they are talking about the quantum internet, in which the quantum internet, you are connecting many quantum computers in the world, and you entangle the qubits of those quantum computers and creating a bigger quantum computer, and you can create the quantum internet, and it is more powerful than this kind of computer. It's like the whole internet will become aware. It will become highly intelligent, far more intelligent than the human race. and that's the singularity. If you could read the book The Singularity is Near, and and there will be another book from Kurzweil, the singularity is nearer, is nearer, is more near, which will be sold in the next year, in September 22, in September 2022. It is okay, my explanation, Sammy.
Yes.
Yes,
Thank you
thank you
very
very
much.
much.
And do you have more questions about it?
Thank you
Thank
very
you very
much,
much,
Juan.
Juan.
Do you have, in the audience, do you have more questions about anything in the slides? It is everything okay? Everything well explained? Some doubts? What time is it? 2 hours. This this webinar have lasted 2 hours.
Yeah.
Prower, do you have questions?
No, it's okay. I think. Okay, we do have a question from audience. I mean, if it's possible, see internally how a neural network identifies edges and shapes while training in computer vision tasks.
Uh, can you repeat the question, please?
So the question is, I mean, if it's possible to see internally how a neural network identifies edges and shapes while training a computer vision task.
Yes. As I said, here is the. Okay. Neural networks are homomorphisms. It means that it projects from highly dimensional pattern spaces to a lower dimensional pattern spaces. It's like a funnel. For example, you have a highly dimensional pattern space here, and you project to this feature space, which is which has a lower dimensionality, and then we have a lower dimensionality here and a lower dimensionality here, and the higher we go in the feature space, these features become more abstract, and they represent more complex cognites, more complex patterns, and yes, it is possible to. Most people believe that due to the homomorphic nature of neural network, the neural networks were like black boxes. But there is an intense research directed to understanding what the neural network learns, and they operate in feature space. So, for example, if there is a correlation in this feature with this kind of pattern shown here in the primary areas, you could go in the opposite way, not in the feature way, but in the reverse way, in the way of backpropagation, and you can infer if this feature is activated, what is the pattern represented in the primary areas in the and it is possible to do to represent in the opposite direction. For example, if the neural network is seeing a car, it is possible to draw the car in a screen. And as I said before, for example, the NF phases and PCA and ICA, you can apply reverse engineering from those algorithms and extract the pattern that is learned, in this case a phase. um, and also, for example, the autocoders are a good example of going reverse from reconstructing the input. It is possible. Yes, the answer is yes.
Yeah.
Yeah,
Okay.
okay,
Thank you
thank you
for
for
answering.
answering.
Okay, do you have more questions, or this is the end?
Yeah.
Yeah,
So I
so I
don't
don't
think
think
there
there
is
is
no
no
more
more
questions.
questions.
Okay, I think that it was a long, very long talk, and I hope that you like it. It is being recorded, and I will publish all the talk uh, in my YouTube account and in the scholarship site in Slack. So thank you very much for your time. I know that this is a very complex topic. I hope you enjoy it, my presentation, my explanations, and thank you so much for your time and your attention. See you. Bye bye.
Yeah.
Yeah,
Thank
thank
you.
you.
Bye.
Bye.